fantastic start. Thanks for everybody's help getting the audio visual working. And thank you everybody for being here. And I guess at some point we'll probably close the doors. So, yeah, happy NIWeek 2015. Thanks for coming. Everybody can still hear me in the back. I just turned it down just a little bit. Okay, so let's get going. What I'm going to be talking to you guys about right now is a template called JKI State Machine Objects. And I wanted to start off by mentioning kind of where this came out of and how we use it, and some of the whys for why we made certain design choices. So in our organization, we do consulting, and we help high-tech companies get their innovative products to market quickly with very high quality. We're often working directly with a team of scientists and engineers helping them be more effective at what they do. So the code that we're delivering to these scientists and engineers, systems engineers, they might be a physicist, possibly with a CLAB, if we're lucky, a CLB, really intelligent, smart people, but maybe not architect level. So the things that we deliver to them, we want them to be highly maintainable, easy to edit and adapt, and again, with very high quality. And we need to be able to rapidly write code so that they can get their technology to market as quickly as possible, because for them, their business is based on that. Hitting their milestones, getting rounds of funding, shipping systems, being successful. So when we talk about JKI State Machine and State Machine Objects relative to other frameworks that are out there, there are some reasons we've made certain design choices. The other thing that I wanted to say from the get-go, kind of related to how we engage with our customers, is we will often bring people in for training on how to use the JKI State Machine Objects, presentations like we're having today, plus exercises. If that's of interest to anybody, if you like what you saw here and you want more of it, you can contact me. Okay. So first of all, who has heard of, used the JKI State Machine before? Fantastic, that just makes me smile. I'll give you a quick overview of the presentation. We'll just, because everybody's pretty familiar, we'll skip quickly through a quick refresher, the JKI State Machine. And then we'll talk about some of the challenges of using the JKI State Machine in a larger project, which are similar problems that we have using any design pattern state machine in a large project. And we'll take a look at what are JKI State Machine objects with respect to the state machines being part of the active object. And we'll talk a little bit more about its use in large systems. This is Murphy's slide. It's okay, I have a backup. We're going to ditch PowerPoint for Mac. We did this on me last night too. And we're going to try to just do this on Windows. Look at that. Perfect. Oh. Okay. Okay. I actually was about to take this slide out because I removed something, but it's ironic. And now back to JKI State Machine. That was Murphy's slide. All right. So a quick refresher to the JKI State Machine. It was really designed for all levels of LabVIEW developers because when we pass this code off to our customers, we want somebody who's kind of new to be able to just kind of poke around and see how it works. We didn't want too many advanced topics, and we wanted everything kind of all in one spot and to take advantage of LabVIEW's editor to help you navigate it. One of the things we found with other design patterns is they kind of spread the different parts of the state machine around into different VIs, and we found that to be very challenging for people to sort of figure out how it works by reverse engineering if they didn't have documentation. And so people wanted a ready-to-run template for creating basic user interface VIs, but also, too, for intermediate developers who want to maintain a scalable design pattern for more complicated processes and architectures. And then at the same time, advanced developers need to be able to have a robust, reusable standard template for even non-trivial stuff. And so we tried to capture and balance all of these things in the state machine objects. So the basic parts, it has a while loop with a case structure inside and an event structure. And the while loop just handles iterating case structure, switches between different states or commands, if you will. And then there's an event structure in the idle frame that allows it to receive either user interface events by default, or you can extend it through the dynamic events terminal to subscribe to dynamic user events that would be coming someplace programmatically. And the dynamic user events is actually a very integral part of the JKI state machine objects template, and is one of our preferred mechanisms for getting events from other active objects. And I'll talk about that a little bit more later. It has a string-based command queue. It uses multi-line strings. Each line is a state, supports arguments and some kind of easy-to-use things that make it easy to kind of read a little macro or script. And I'll show you an example of that in a minute. And there's a case structure frame for each command, and a cluster of data in a shift register, and an event structure that's called when the command key is empty. So again, I'll just go back to the previous slide here. You can kind of see there's a while loop, case structure, event structure. The top pink wire contains a cluster of data, and the bottom wire is a string. It's a multi-line string, and we just pop an element off the string, and that chooses which case of the case structure is going to be invoked. And we just do that until there's no more states, and then the idle happens, and the event structure is called. Other people in the community have modified this template. Some people have pulled the event structure out and to the left so that an event gets handled, and then all the work happens, and then it kind of loops back around. So there are different variants of this the community has used. This is just a general good starting point. Let's jump back ahead now. Okay, so we've used the JKI state machine, and we have some VIs that we've created. And what naturally happens is you'll have different state machines in different parts of your code, and there are challenges that occur. So we start adding more, and we find that we want to be able to communicate between the different state machines, but what's the best mechanism? And there's actually lots of different mechanisms, and if you saw in 2015, now there's asynchronous wires, and you could theoretically just, or literally just wire an asynchronous wire between JKI state machines, and that's really cool. And maybe we'll take advantage of that in the future. One of the ways that we've chosen is using what's called public events. And when I say public, what I mean is once we kind of wrap this in an object style template by reference object, we want other objects to obtain reference to public events. So for example, if I have a stage that uses a motor, and the stage wants to know when the motor stalls, the stage, which has a motor reference, can get public events and register for the motor stall. And the stage's asynchronous process can be just waiting passively for notification or when the event happens of when the motor stalls. It doesn't have to continuously poll the motor will just tell it. And so I'll show you guys some templates for that in a few minutes. So let's just kind of list off the various challenges of building an application that has multiple asynchronous processes. First is dynamic creation of instances. If I've created a class or component, which is a stage, and then I have a larger application that has 2 stages in it, the way that beginning developers will often address that problem is they'll make a copy of the code. One VI called stage A and another VI called stage B. Or if they're not even using VIs, they might literally just copy the whole JKI state machine into another part of one big VI. And so dynamic creation of instances, what that means is we can have a VI called create stage, and that will somehow spin up a new instance of the state machine. I'll show you guys some examples of that in a minute. Starting, stopping, and synchronization of instances. As we start creating multiple asynchronous actors, basically, synchronous loops, there are some times when we actually do want some synchronous behavior, especially at startup. If there are 2 components that kind of need to communicate with each other, they kind of both need to be initialized and ready at the same time. And so what we learn when we try to do that is we realize by making mistakes that we haven't accounted for these things. We learn the hard way that these startups and shutdown synchronization issues can really get us. And they're corner cases, really. Passing in initialization data. If something is running asynchronously, how do we kind of get data over to it? Messaging into, out of, in between instances. We talked a little bit about using public events to do that, or different mechanisms, queues, network shared variables, anything. Managing a whole system of instances. And there are really a variety of solutions, and a lot of people have developed good solutions. One of the things we want to avoid is reinventing the wheel, and another thing we want to avoid is being subjected to the corner cases when we least expect it. And so what I definitely found when I started exploring kind of building these types of frameworks about 10 years ago is that we only realized the corner cases 6 months into a deployment, and some reference went invalid, or we started something, but for some reason we started it, but it didn't get the event. But we know the event was sent, so how come it didn't get it? Oh, but it wasn't listening yet. And so when we look at the implementations of these solutions, the code isn't extremely complicated. But thinking about these corner cases ahead of time, if we haven't hit them before, can catch us off guard. And debugging these corner cases can also be extremely challenging because most of them are race conditions. And because they're race conditions, it means they're very hard to debug because they only occur intermittently. So we really need good design patterns and templates for doing this. And so I'll introduce you to the concept of the JKI state machine objects, which is really using the JKI state machine as an active object. So in this concept, the JKI state machine is the active part of a by reference object. And I'm sure several people in the room have played around with by reference object frameworks. If you're not sure what I'm talking about, an example of a by reference object is a queue. You can create a queue, perform operations on it, you destroy the queue. You can create several of them in parallel. You can have the constructor for the 10 of them. And so we're talking about the JKI state machine. When we create the object, there's now an active loop, a JKI state machine, that actually has that same reference to the object and all of its data. So when we create the JKI state machine, somewhere in the background that we don't necessarily see unless we have that state machine configured to open this block diagram, it spawns an instance of the JKI state machine. When we invoke the start method, it starts the state machine running. And that JKI state machine will keep running in parallel to your main application. The main application kind of below the JKI state machine is basically, this is kind of like the user. So for example, if a stage needs a motor, a stage might create the motor, or the motor might be passed to the stage because it's dependency injection. And it'll just interact with the reference, but it never even has to know that there's an asynchronous VI. There's no blocking VI called run the state machine and it's blocking. It just happens behind the scenes. When we hit stop, the state machine is sent a message to stop. And then when we call the destroy, the state machine goes away. And when I say the state machine instance is created and the state machine instance is destroyed, what I mean is the VI that has on this block diagram the JKI state machine. So again, this is useful because it addresses dynamic creation, multiple instances, lifetime management, startup shutdown synchronization, and hiding the complexities in a common base class, which are these VIs that I showed you to create, start, stop, destroy. Having all the complexities of managing passive initialization data, startup synchronization, shutdown synchronization, how we message starts and stops, destroying all the data. It's kind of nice to have that all hidden behind 4 very simple functions. And if for some reason there's a bug or an enhancement, those can be made at the base class level rather than each copy of the template. So basically it improves maintainability, robustness, and reusability of the components you build. So that's great. But what about active framework? And so this is a question that we get a lot. And so I think it's helpful to, first off, kind of say that there's really no better or worse kind of globally. It kind of depends on what your needs are. And I mentioned before JKI's needs in terms of helping it also being accessible and useful for new developers who need to be able to just jump in and poke around and see how everything works. The NIActor framework and the JKI state machine mostly solve the same problems in different ways. And the JKI state machine is basically a queued message handler, where the queue is local to and private to the wild. And so we saw the string on the shift register. And I've seen some people violate that by having a frame of the event structure or somewhere that's waiting on somebody else to pump strings into it. So we've actually exposed the ability externally to send commands. That always troubles me because it's like, where are they coming from and who's sending them? And now I have to document or explore to find out how the code actually works. By keeping it local, I know that just by browsing through the different frames of the state machine, I can find every place that's adding new states. One of our best practices also is to not put those state enqueuing in sub-VIs, because if they're exposed on the block diagram of the VI that contains the state machine, you can use the LabVIEW search tool, like Control F find, and you can search for state names and specify the scope of that search to be just this VI, and it'll find all instances and you can quickly navigate around to figure out how your state machine works. And again, too, I'm just driving to one of the challenges that I personally have in my LabVIEW development, reading or understanding code that was implemented with the queued message handler, is I kind of have to go exploring to figure out how the state machine works and who's sending events in. So the NIActor framework is really an extension to an evolution of queued message handling, where an actor is basically that main while loop of the queued message handler by reference, and every frame of the state machine, of the case structure, is now moved into a VI, actually a class, right? A new message type that has the do work. And so it's extremely powerful, but again, to really understand how this works, we're now actually, every frame of the case structure in the JKI state machine, if you look at the actor framework, we're now looking in classes, popping open all the VIs, figuring out like who's sending messages where. And I found it personally hard for me, and I know for development teams, it's challenging onboarding new developers to the actor framework. That being said, the actor framework is extremely powerful. If anybody saw this morning Tony Milo's presentation on the actor framework, we use the actor framework for one of the big applications we developed that won an Engineering Impact Award, where we had 14 different systems and we needed networked actors. And the degree of flexibility and decoupling the actor framework provides for product line engineering especially is exceptional. But handing this over to a systems engineer who might be a CLAD, the JKI state machine and state machine objects we have found to be extremely easy to get up to speed. So state machine objects adds object orientation to the JKI state machine in a similar way that actor framework adds object orientation to the message handler. And actor frameworks actors can also be used for messaging into and out of JKI state machine object processes, and state machines can be used inside of actor framework cores. So there's really no better or worse. You can mix and match. It really depends on what are your use cases, what are your requirements of your software, both short-term, long-term maintainability, long-term flexibility, scalability, and who are the developers that are going to be doing all this. Okay, so we'll start a quick demo and we'll get to some code. VI, that's you drag it and drop it off of a palette. And it's in a VI, you name it process, and then you can add it to a class. And you can see here that this VI is just simply contains a JKI state machine. And then what you do next is you set its inheritance so that it inherits from the JKI state machine object base class. So now, because it inherits from the JKI state machine object base class, we can take your class, which is the one that we just created here, and this is just a little example. I call it basic by value JKI state machine object. We have our class reference, and now we're calling the base class methods to create, start, stop, and destroy, and everything under the hood there is doing the work of spinning up the VI with the state machine, telling it to start, telling it to stop, and destroying it. So it's pretty simple and straightforward. So the other thing that we really wanted to do with this framework was to provide a programmatic API for developers who might want to build tools to make editing and maintaining of these classes that you'll be creating. And so we have a variety of functions, and I'll actually show you one of these in action in just a second, for creating new JKI state machine objects. So these aren't VIs necessarily within the framework. This is a scripting API for dynamic creation, editing, maintenance of your classes, which are JKI state machine objects. And the primary target user of the scripting API would be people creating like LabVIEW project environment plugins or little editor helper tools. Okay. And we built a very simple editor for prototyping this, which allows creating new classes. And we'll actually show you which objects have processes running. You can just double click it to open. So I'll actually show you that right now, the scripting. one of the things that we found with a lot of these by reference frameworks or class templates, how many of you guys have like a component template that you've developed or used? One of the things that's always I found challenging is as you start making copies of your template code, it becomes, you typically have a template that has everything you could possibly need. And then what ends up happening is all of your code has like 2 or 3 times more code than you actually need just in case. And what we really wanted was a scripting API with a set of editor tools so that you start out literally with nothing and you can just build up the pieces that you want. Or if you have an existing VI with a state machine, you can say, well, I want this to be an object now, and then it would just wrap it in the class, set its inheritance, and we can do it all programmatically. And in fact, if we have a new version of JKI state machine objects, and maybe it's made improvements to some of the parts that still kind of have to be template, that it can do programmatic upgrades and maintenance of the code for you as well to bring your instances of those templates up to date. So this is my first demo of NIWeek, so I'm going to keep my fingers crossed. I heard a demo this morning didn't go great, so we'll see if Christmas. So what I'm going to do here, I did a dry run of the demo to increase my odds of it working. So now I'm going to delete those guys. You can see they don't exist. And I'm just going to single step in here. And so this first function will basically create a new class, state machine object, and we'll skip over and we see, hopefully, there we go. So now I have a new class and there's literally nothing in it. And then we'll let this continue executing here. And it's going to check to see if it is a JKI state machine object. And it says false. It's not a JKI state machine object yet. And the reason why it's not is because it doesn't inherit from JKI state machine objects. So if I show the class hierarchy, we can see that it's just simply a LabVIEW object. Okay. Actually, I'm going to move this up here so you can see. And then as I step over this, the moment it calls that function, all of a sudden we see that there's a new class in the inheritance hierarchy, so we've made it a JKI state machine object. And then it's going to see, does it have private data? And it will add private data, and you can see if we look at the class. It now added this private data cluster, which is where you can put data by reference. So any new method that you create will have access to this private data. And then it also can add public events, etc. So that's just a simple example of using the scripting API to programmatically create a new instance of the JKI state machine object. And if we open this up, I'll open it. So let's get back here. Yeah?
How did you know that you had private data?
Well, the scripting API checked to see if that class had private data as a feature of the class.
So you have to create the class first. Who creates the class?
Well, the programmatic scripting API created an empty class. It made it inherit from JKI state machine object, and then it checked to see if it had the private data feature, meaning it had data by reference, and it did not yet, and so it called the function add private data, and it scripted the feature of adding private data plus the constructor destructor. So if we look here at Jim's class, you can see it added a constructor here that added private data by reference, so it got a reference to that data, it constructed it, popped it back into reference. Close that here, there's the data by reference. So now that data is actually accessible to any public method. So now, messaging between JKI state machine objects. So I'll leave it on this for a second, but I think in order to really kind of grasp it, you have to kind of see the code. Basically, how many people have seen the public-private events presentation we've given in the past? Okay, good. I'll describe exactly what that is here in a second. And I think the best way would be to show you guys in the code. So let's open this up. So this is a JKI state machine object that has more features that have been added to it through the scripting API. And one of those events is get public events. And the way that this method works is it outputs a cluster that contains dynamic events. So if this were, for example, a motor object, and we call it get public events, there it would have, for example, an event called motor stall. The stage, if it has a motor reference, could call this function, get public events, wire that up to the dynamic, or wire it up to a register for events, and then wire it into the event structure, and then get notification. So this code is broken, but what I'm going to do is just kind of in general show you how the design comes to it. So what we can see here is we've created an instance to the object, and then we've invoked the get public events. And then we call the register for events node, and then pass it into an event structure. And then here, we're waiting until that event has occurred. And so one of the things about this framework is that if you have a single motor, and if there are several places in the code that need to subscribe to that, so for example, the stage is a low-level component that needs to know if the motor stalled. You might also have a user interface for the motor that needs to display on the front panel whether or not the motor is stalled. So both the user interface, which is a state machine, can be a state machine, can subscribe to that event, and the stage can subscribe, and other actors can subscribe as well. The motor doesn't have to know anything about the stage or the UI. They just need to have a reference to the motor and subscribe to the event. So this is a one-to-many publish subscribe, where the publisher of events doesn't know anything about the consumers of the event. And so by doing that, we have a lot of decoupling of our components, which allows development to be a lot easier. When we decouple our components, what it means is when we make changes in one spot, it doesn't really have so many trickle-out effects. The only trickle-out effect would be if we change like the data type of a motor stall event. Versus, for example, actor framework is often basically, it's about something from the outside kind of pushing events in. What I've found is for by reference objects, this idea of public events, which decouples the producer from the consumers in a one-to-many way, is extremely flexible, and you can have many user interfaces open simultaneously, waiting on subscribe to events. And when something happens in the system, the state changes, they all just kind of magically update. And there's zero processing overhead, figuratively, associated with having all of these VIs just kind of waiting in an idle frame for an event to occur. But the event occurs and they all update simultaneously. And this is really the way you want to design scalable systems. If every loop is polling for state changes, then the bigger your system gets, the more things that are polling. It doesn't really hurt the system design to have more things just waiting for a notification. It scales much more naturally. So what I was going to do is show you now, inside the process, some of the plumbing that we have. So this process that I'm showing you, I'm going to hide a couple things off to the side there. So part of the macro initialize, if you're familiar with the JKI state machine already, you're familiar with the idea that there's a macro initialize. It's a little bit different in this template for JKI state machine objects because it has this events register. Can everybody see, or do I need to increase the screen resolution? Let me try it and see if I... Oh. A little bit better?
Yeah.
All right. So we have this new, a couple new frames. Events register and a process sync. So events register has some event registration going on. And the first thing that it does is it calls some base class events. So the JKI state machine objects base class that has the create, start, stop, destroy also provides a get protected events method. And we're calling that, and that allows the base class to send events like shut down, stop, because somebody invoked the stop method. And we also call our own level, meaning if this is a motor object right here, it would be calling motor get public events, which would then allow us in our state machine to subscribe, if we wanted to the motor stall event, because it might be someplace else in the code that the motor stall occurs, or it might even be another frame of the state machine. What we do in our template is we pre-register for all the events. Yeah, John.
Where do you define public events for
Okay, so that happens in the constructor, and I can open that up. Let me open that up now. That's a really good question. Yeah. So in the constructor, where all the references are created, there's a VI called create public events. Change it for you. Can't be putting that on. So in Create Public Events, here we have our public events data. And I can, so we create the user event and then we just pass it into the data structure. And then the VI that gets public events, all it's doing is unbundling that and passing it out.
So
Yeah.
it's just a user event that everybody else has access to.
It's just a user event that everybody else has access to. And by everybody else has access to it, what we mean is that this VI, Control Shift D, is a finding project. It means that this is a public method of the class. So that gives stage the right to call the get public events of motor. We also support private events or even protected events. So you can add these features to your state machine object class. It's often nice to be able to have events that are protected that only your children can access, or even private events that you're just using internally for your own messaging. So right now we're subscribed to our own public events, but if we want to listen to events from other objects in our system, we can just subscribe to them in here. And one of the really, really nice things about this style or design pattern is if we just plunk down a get public events or get protected events, and we wire it into the register for events. And we go over to the event structure, and we pop up here and add event case. Those dynamic events, for example, here's the JKI state machine object base class protected events, and here's our own public events. This would be like motor stall event. They just automatically show up in the event structure. And if I'm a stage developer and I've got a motor, and the motor developer has a new release of their motor, they release motor 2.0, and motor 2 has some special new feature and has some special new events. Once they add those public events inside of that get public event structure, they automatically show up in the event structure frame of anybody that's subscribing to them in this register for events frame. And so as we were kind of designing this design pattern, the getting stuff for free from the way LabVIEW works is one of the things that we go for. And for us, this was a very natural way to do kind of message subscriptions in LabVIEW. Now, one of the things that I will say is that this design pattern had a lot of challenges associated with it when we first started implementing it, just because of bugs or features in the way that events were used. I don't think we were using events the way that they were intended to be used. But also, too, there's some kind of gray areas. Right here, we register for events. This is basically creating a queue for us that will get filled by the event producer, even though the event producer doesn't know about our queue. There's some magic behind the scenes of the user events frameworks that kind of handles the whole publish-subscribe system. So there's actually a queue that gets created, and anytime these events get generated by the producers, they fill up the queue. And then what happens is the event structure dequeues, it handles the queue. Well, it used to be the case in early versions of LabVIEW that had dynamic user events. If you registered for events, but your event structure didn't actually have a case that handled them, that queue, your mailbox would get fuller and fuller and fuller to the point where you weren't getting the mail you wanted. Since then, they've added a feature that every time the event structure gets back to its kind of wait on events, it knows which frames it has DQs for, and it'll flush everything else out of it that this event structure doesn't handle. And so through this design pattern, we actually there was an evolution that happened. A lot of bugs got fixed as well, so I'm pretty happy to say that it's very stable and useful today, and it's very performant as well. Okay, so kind of back to the storyline. So because we're subscribing inside of Events Register, we get those for free. They just kind of show up automatically inside the event structure when we want to add them. And it's just a very nice way to do development. The API, we're also going to be adding features that can allow you to declare a dependency on another object. Let me see if I can show you that now, because this is another kind of critical part to where this is all going. So this framework has a concept of dependencies. Let's pretend now we're not in motor, we're in stage. And so in stage, we might want to declare a dependency on a motor object. So we could come in here, drag and drop motor. And now our stage has a place to store its motor reference. And if we then go into the process VI, and we want to register for events on the motor, what we can do is call the get dependencies method. And I'm not going to use proper coding, style, error handling, or any of that for this demonstration. And then what we'll do is we'll call get public events. Now I just drag and dropped my own, but let's pretend for a moment that we're actually calling to get public events of the motor. What we would do is unbundle our dependencies on motor and wire that up to the motor's get public events, and then come over here to the event structure, pop up add events, register for motor stall. All those little steps that I'm showing you can very easily be scripted as well. If I am working on stage and I say, I want stage to depend on motor, we can automatically do that for you, drop the get dependencies, drop the get public events, wire it up, and now you're literally just going over to your state machine's event structure and choosing which events you want to subscribe to. Okay. One of the next steps that I wanted to talk about too was dependencies and dependency injection. And as we get into large systems, we'll often find that we don't want our stage in charge of creating its motors. We don't want the stage configuration data to necessarily know what type of motors it has and what their configurations are and what all their V support numbers are, because that makes our stage component much less flexible. If I have a stage that knows how to interact with motors, and I have a stage jog pad that knows how to interact with the stage, it's very nice to be able to make improvements to my software such that it can handle servo motors, stepper motors, linear motors, other motor types, and for my stage jog pad and my stage code to not care what type of motor it's working with. However, if the stage is in charge of creating it, the pattern we might find is that, we have an input with an enum that says, well, do we want a servo or a stepper, and then we'll have a case structure that constructs that. But we'll often find that it's nice to have a VI, maybe that's like your high-level application that's creating all the components. So for example, if we're calling create, and for a second here, we'll pretend like these are different object types. So maybe I have a stage that has a servo motor and a stepper motor, and I want to create all of these guys. And see why I didn't enter the fastest coding competition. It's hard to do it on the track. Okay, and then we'll create the stage. And then let's go into the stage's dependencies, and we'll edit this. And for this example, what we're going to do is we're going to say that this stage has an X motor and a Y motor. And we'll call set dependencies. Create constant in that diagram. And then we'll bundle these guys up. So this, what we're about to do is called dependency injection. And this concept basically means that the stage's dependencies are going to get injected into it after it's created. And we'll pretend like the stage UI needs to have a reference to a stage. Let's just pretend for a second that that wire is not broken. So here we're creating a servo motor and a stepper motor, a stage and a stage UI. And then what we're doing is we're passing the stage a reference to the two motors, and the stage UI a reference to the stage. And then once we've done that, we can then, let me find my, here's the state machine object. I can call start on these guys. And once everybody has their dependencies, we then invoke the start method on all of them. Probably after we set their configuration data. And so there's actually a method for that in the class template as well. Set dependencies, set configuration. So we'll probably call a set configuration data on each of these to pass it some configuration parameters. For example, if each of these motors has a COM port, I'm doing the quick drop shortcut for wire. So, and then what we'll do is if I kind of move on, we'll call the destructor. So this VI here would basically be kind of equivalent to my top-level main or my splash screen. And there's a lot of steps further we can go. I'll leave that open for just a second. So configuration data and configuration data injection. We can see here we've got config data we can pass into each of these things. So now my top-level VI can pass configuration data.
Where's that configuration data? Is that like in the cluster?
Right now it's in a cluster there, but there are ways to do it as variant or XML. And there are also things like factory patterns for system instantiation and startup. So there are, and we do have, for example, like a system class that can basically instantiate, do the instantiation and dependency binding. For example, from an XML-based configuration, it can read an XML file. It can look at what are the objects that you have, how are they dependencies bound to each other, and say, okay, we've got X motor, Y motor. Everything I just did on the block diagram, there's a pattern, a generic abstract pattern associated with that. So I've already done the demo. And I'm kind of in wrap-up mode right now with respect to kind of how this works. But I hope you got kind of the main concept of how each object or component in the system will have its own public events, and other objects can basically declare those objects as dependencies, get their public events, register, subscribe to them, and then get asynchronous notification in a publish, subscribe, one-to-many fashion that decouples the components in the systems in a very nice, scalable way with very good user interface and programmatic response. And then the state machine objects framework itself is kind of designed to just make that as simple as having a JKI state machine that you want to make a JKI state machine object, and then have a user interface tool that can allow you to add new features to your objects. Part of my wrap-up, I'll talk about a little bit of what we learned, and I think I've kind of already done this, except the final bullet, which is to say, this is all open source, and it's our intent to open this up to the community so that you guys can better maintain your code. We also, the JKI state machine has always basically been open, but we've actually recently released it in the springtime under the BSD license. The JKI state machine objects framework and all the stuff that we develop is also BSD licensed. We've got a lot of stuff that we've been refactoring. We have a lot of, let's say, internal frameworks and tools that we're basically trying to clean up and get that out to the public. But we're working to build an active community around it. We really want to get you guys involved, and there's a couple ways that we really want to do that, which is to encourage people, if they're interested in doing development, for example, using the scripting API to create high-level tools, that's one area. If you're passionate about the JKI state machine, and maybe you've got your own VIs that you customize, the features, we'd like to hear more about that at the developer level. But also on an ongoing basis, I'd like to be doing kind of online user group meetings where we can meet over GoToMeeting and hear from people about how they're using it, things that they want, and then with the developer team as well. Plus doing some webinars like today's presentation, kind of some of the getting started and key concepts, having webinars online that people can watch the videos at their own pace. Feel free to email me, also our JKI contact stuff. And then kind of a final note, I'll mention, we are hiring, we're extremely busy, we're doing some exciting stuff. You won't necessarily get to work with this guy on the left there, but these are just some of our fun pictures from NIWeek, and you can find out more information about the different positions that we have available. But as you can see, we're extremely passionate about LabVIEW. We have been for many years. sharing the tools that we use to help our customers with the community, these tools that we're using to help our customers get their products to market very quickly with high quality. And it's just been a pleasure presenting to you guys today. So thank you very much.